enrichment, special quiz 2 is on the board. You should be able to download it with no trouble since it's 8.5 by 11. 2 pages. Get them both. On with our intention to get delta G for a reaction, delta G for the reaction under standard state conditions, delta G sub R super 0, and K the equilibrium constant for the reaction connected to each other. First, make sure from a practical standpoint, you are aware of the difference between delta GR and delta G0R, which we've discussed previously. Delta GR refers to any possible set of conditions. Delta GR super 0, strictly standard state conditions. A defined specific set of conditions. For example, in the past we asked you to recall the experiment you did in 45 laboratory assignment 4, where after having observed that the conductivity of deionized water as measured with your handheld conductivity meters, 0. But you put together sodium carbonate solution with calcium chloride solution, made calcium carbonate. Separated calcium carbonate from the reaction mixture by precipitation. Washed the calcium carbonate so as to purify it. And took a little bit of the purified calcium carbonate, stirred it into a fresh 50 milliliter sample of deionized water. Stirred it up thoroughly. To, in short order fashion, prepare saturated calcium carbonate solution and reobserve conductivity. And on reobserving conductivity, you got an on-scale conductivity reading. That means when you stirred the calcium carbonate in the deionized water, some of the calcium carbonate dissolved. All you did was really add it to the deionized water and stir a little bit. So the calcium carbonate dissolves spontaneously, which means delta GR for that transformation, the dissolving of calcium carbonate, at a negative value. But what about delta G0 for that transformation? That's a whole lot different. This calcium carbonate dissolves spontaneously in a solution in which the carbonate ion molarity and calcium ion molarity are each present and at 1 molar. Can you make this system, calcium ion, carbonate ion, together in the same water solution at 1 molar concentrations? Impossible. Because as soon as you get the calcium ion molarity and the carbonate ion molarity to be values above the saturated solution molarities, which is on the order of 1.4 times 10 to the minus 4, at least that's for calcium ion. Carbonate ion molarity is about half of that. We've already done the arithmetic to verify that. Any molarities above those values, calcium ion and carbonate ion react, and boom, out comes calcium carbonate. So from a delta G0 standpoint, calcium carbonate certainly does not dissolve spontaneously. It forms spontaneously under standard state conditions. Water solid, water liquid. At 0 centigrade, external pressure 1 atmosphere, delta G0 for this transformation is 0. This you should realize from our analysis of the phase diagram for water liquid. Because under these conditions, The standard free energy of formation of water solid and the standard free energy of formation of water liquid are equal. How about this equilibrium reaction? For what set of conditions is this equilibrium reaction, is this reaction at equilibrium under standard state conditions?
1 degree centigrade at 1 atmosphere pressure?
What do you mean when you say 1 atmosphere pressure? You got to be more specific than that.
1 atmosphere partial pressure of the water vapor?
That's right. Because at 100 degrees centigrade, what's the vapor pressure of water liquid? 1 atmosphere. At 100 centigrade. So in order for this to be in equilibrium under standard state conditions, the partial pressure of this, I don't care about any external pressure. I don't care if you apply 1,000,000 tons of pressure to water liquid. If there's no water vapor above it, this stuff's going to evaporate. And now the tendency for this to evaporate, vapor pressure 1 atmosphere, and the tendency for this to condense, partial pressure 1 atmosphere, are equal. So now this is at equilibrium under standard state conditions. That means delta G0 is 0. There are very, very few equilibrium transformations for which delta G0 is 0. But there's a couple of examples. Now then, back to the arithmetic aspect of getting these 3 very important thermodynamic terms connected. Consider a hypothetical reaction. 2 moles of X, whatever X is, dissolved in water, reacted with Y, gas phase material, to produce Z, also an aqueous solution component. Studied under conditions for which the molarity of XAQ is not 1, the partial pressure Y gas is not 1, and ZAQ is not 1. So under this set of conditions, is this system being investigated in the standard state? No. Because all of these would have to be 1 if you're going to investigate this in the standard state. For this system, under the indicated conditions, or under any set of conditions. I should have written that. For this system, under any conditions, we define a term. You've seen this term before. We looked at it in chapter 17, in brief, when we talked about fundamental aspects of equilibrium, and again at the start of chapter 19. Semi-soluble salt EQ. Because for semi-soluble salt EQ, the Q term is the molar concentration of the cation of the semi-soluble salt, like calcium ion, multiplied times the molar concentration of the anion component of the salt, carbonate ion, for calcium carbonate. Because for semi-soluble salts, if the Q term, calcium ion molarity times carbonate ion molarity, is bigger than K, the equilibrium constant, what happens? Precipitation forms. So here's where Q comes from. It's just a term defined which has exactly the same form or composition as the equilibrium constant, except Q corresponds to any imaginable set of conditions. Any possible set of conditions. So here's Q for this system. When is Q and when are Q and K equal? When these are all equilibrium values. Nothing fancy about this. We've already done this. If you can write K, you can write Q. because they're the same thing, except for the values contained within. Because when the system's at equilibrium, all the concentration terms, all the partial pressure terms are equilibrium values exclusively. Now then, as I said, this relationship is on the information sheet. It's in the notes. We take it as a given. It can be derived from fundamental thermodynamic considerations, and some textbooks do this. I don't feel like taking the time because we have to go through and reconsider, as the case might be, because you might have did this in 2045, but I don't think you did. Properties of gases. I don't want to take the time to do it because, again, at this stage of the game, as I see it, we should be interested in the application and understanding of the significance of these terms rather than their derivation. If you take an upper level course in physical chemistry, you will of course go through the derivation. At least that's what I would expect. Change in free energy for a reaction is equal to the standard change in free energy for that reaction plus RT natural log of Q. And when a reaction is at equilibrium, delta G is 0. And when the reaction is at equilibrium, Q is equal to K. So that gives us this for the system at equilibrium. So I don't have to keep writing this. I'll call it circle star for convenient reference. This is important because direct measurement of delta G0 for reactions is tough. For many reactions, we can directly measure delta H0 by calorimetric studies, combustion reactions, the likes of which you discussed in 2045. But measuring delta S0 directly, that's not easy to do. The upshot of which is if I want to get delta G0 for the reaction, since it's difficult to measure delta S0, I have a problem. But with this relationship, the problem is eliminated. Because measuring the equilibrium constant for most reactions is not difficult. Now, it is true, we'll talk further about this in the next chapter, chapter 22, that equilibrium constants are very commonly evaluated by electrochemical measurement. So we'll talk more about that next chapter. But for example, if you want to get delta G0 for the dissolving of calcium carbonate, well, let's go make saturated calcium carbonate solution. Measure the temperature at which the solution exists. And then get in there and measure the calcium ion concentration and carbonate ion concentration and multiply those two values together, and what do we got? We got KSP. Isn't that K for dissolving calcium carbonate? So we put it in there and calculate delta G0 for that transformation. So this is a very important term because it allows us to get at a whole collection of delta G0 values for reactions should we be able to determine K for the reaction. And determining K is oftentimes not a problem because when the system is at equilibrium, as long as we keep the system isolated and insulated, does the system change? No. Heck no. Don't have to worry about kinetics. Don't have to worry about time. We got saturated calcium carbonate solution. We'll measure the calcium ion molarity and then we'll go to Burger King. I need a Whopper or whatever you want. Come back later in the afternoon and then we'll measure the carbonate ion concentration. So, let's see what we can do with this relationship. Let's see what information we can get from it of a practical nature. Well, let's go back to teacher's favorite stuff. Calcium carbonate. But this time, rather than consider calcium carbonate dissolving in water, because we've already done a great deal of analysis with that system, haven't we? KSP calcium carbonate calculations, we've done a whole bunch of that in chapter 19. Let's talk about calcium carbonate, the pure stuff, not being treated with water, but imagining it to decompose into calcium oxide solid and carbon dioxide gas. Let's imagine this transformation firsthand to take place at 25 centigrade, external pressure 1 atmosphere. There's the equilibrium constant. We know that because in equilibrium constants, concentrations of solids are not included. So the equilibrium constant for this reaction, thermodynamically written, is simply the partial pressure of product CO2 gas. Let's go to table 1 at the end of chapter 20. And look up. Delta H sub F super 0 for each component of this reaction system. Delta H sub F super 0 for calcium carbonate, calcium oxide, CO2. Well, we can look all those up in table 1. You can do this for arithmetic practice. And we'll also look up the standard molar entropies for these materials. And then with these data, we will apply Hess's law, from which we will get delta H0 for the reaction and delta S0 for the reaction. And then with the relationship delta G0 equals delta H0 minus T delta S0, we calculate delta G0 for the reaction. Well, the puzzle parts are this. Delta H0 for the reaction, I get plus 177.5. And I've been sharing this data point with students now for 30 years. Nobody's argued with it yet, so I have a strong feeling it's correct. Same for the delta S0 value. So these data as it stands show us that the standard change in enthalpy for this reaction is favorable or unfavorable? Unfavorable, endothermic. But the standard change in entropy for the reaction shows us favorable. Well, which fundamental puzzle part of this system is controlling the outcome of this reaction? You see this coming apart in the CO2 right before your eyes? Question? So it follows that. When we calculate delta G0 for this reaction at 298 K, we get a positive number, plus 129.0 kilojoules. And that delta G0 value is positive because the absolute magnitude of delta H0 is greater than the absolute magnitude of T delta S0, even though this wants the reaction to go. This says no. And this term is bigger than that term. So the no factor outweighs the yes factor. The no-go factor outweighs the go factor. So if we had this system before us under standard state conditions, which means we'd have calcium carbonate solid, calcium oxide solid, and CO2 gas at what pressure? 1 atmosphere if we have the system under standard state conditions. And the temperature is 298 K, what's going to happen? The calcium oxide will react with the carbon dioxide and become calcium carbonate. Well, let's get the equilibrium constant for this transformation. We already know what kind of value we're going to get relative to 1. What kind of value will we get relative to 1? Smaller or bigger than 1? A hell of a lot smaller.
Could you get the reaction to be spontaneous at a higher temperature?
Well, just a minute, we'll get there. Don't worry, we're going to heat the hell out of this and then see what happens. So here's our K calculation at the temperature 298 K. I put in the numbers. For convenience, I left out the units. This is R in joules, because you got to make sure the energy units on delta G0 and R match. I've seen students follow this up because they put in here the R value that has the units of liter atmospheres per mole K. That won't work. Even though liter atmospheres is a legitimate energy unit. Not a common or convenient one, but nevertheless an energy unit. Now then, from this arithmetic, we will get this numerical value with no units. So numerically, K for this transformation at 298 K is 2.3 times 10 to the minus 23. But if we're going to do anything practical with an equilibrium constant, we need units. Where are we going to get the units? Because when you calculate a K value from fundamental thermodynamic information, like the information in Table 1, you get no units. Where do you get units for an equilibrium constant should you need units? The reaction, period. The equation for the reaction gives you the units. So what are the units on this reaction? Given that we will use atmospheres rather than bar for pressure. So what's the units on that? Atmospheres. Okay? Units? Atmospheres. What if I did this arithmetic for the same reaction but with these coefficients? We asked you to think about stuff like this back in chapter 17. I can put any coefficients I want on reactants and products, so long as they keep with material balance and charge balance. If I calculate K for this reaction, will I get the same K value? What K value will I get relative to 2.3 times 10 to the minus 23? I get the square root of 2.3 times 10 to the minus 3. What will be the units? I'm listening. Atmospheres to the 1/2. Well then, rather than being skimpy, I'll be generous. Is the numerical value K for this reaction bigger or smaller than 2.3 times 10 to the minus 23? Smaller, because it's 2.3 times 10 to the minus 23 quantity squared. And the units? Atmospheres squared. Bingo. Now then, back to the practical considerations which we can make for this system. From the thermodynamic arithmetic which we have so far done. Before you, I ask you to imagine the presence of a 10-liter flask. Now, we are going to be sure that this 10-liter flask contains no CO2. I don't care if it's got oxygen, nitrogen, I don't care about those things. As long as they are gas phase materials which do not react with the components of this system. Oop. Let me go back to the coefficients we want. This is calcium carbonate. It is calcium carbonate, isn't it? Yeah, that's what I just wrote with. Huh? So I'm going to put some calcium carbonate in my 10-liter flask, which is absolutely devoid of any CO2 molecules. Temperature is 298 K. What will happen regarding the calcium carbonate? Will the calcium carbonate decompose? The flask is devoid of CO2 molecules. Are we under standard state conditions, or are we under Q conditions? What's going to happen? Will the calcium carbonate decompose? Yes. When I put the pure calcium carbonate into deionized water in a Simon Ford 45L, did some of the calcium carbonate dissolve?
Yes.
I didn't ask you how much. I just asked you if some of it dissolved. So here, if I place my calcium carbonate in this flask, which is at a total pressure of 1 atmosphere, because of the gases acting above the calcium carbonate, but none of these gases react with the components of this system, which means that none of the gases at the minimum are CO2. So will the calcium carbonate decompose? You're damn right. How much? So here's the question. How much CO2 is obtained? Well, let's go back to my Van Gogh representation of our experimental system. If you want a copy of this, I'll autograph it for you. Small charge, of course. Got to get some beer money somehow. Okay? And ask the question. Number of CO2 molecules obtained. How are we going to calculate this?
Ideal gas law?
Yes. You think it's fair to treat CO2 as a gas which obeys PV equals nRT? Yes or no?
Yes.
Why? Why yes? First of all, we're at 25 centigrade.
It has volume and pressure and temperature.
What properties are shown by a gas if its behavior is describable by PV equals nRT?
The particles have constant random motion. Perfectly
Have what?
kinetic, constant random motion, perfectly kinetic. That says they have negligible mass. So negligible volume.
Mass of CO2 molecules not negligible.
Volume. And no intermolecular forces.
Aha. Intermolecular forces. What kind of intermolecular forces exist among and between CO2 molecules? London forces, because these molecules are not polar. At 25 centigrade, do you think CO2 molecules demonstrate much tendency to associate with each other and become dry ice? So PV equals nRT will suffice. So I'll solve it for N. Our flask has a volume of 10.0 liters. What R value do we now need to use? The R value in liter atmospheres. And we said we are going to take a look at this at 298 K. What do we put in here? Yes! That's the partial pressure of CO2, isn't it? when this system achieves what condition? Equilibrium. So what we're really doing with this calculation is find out how many CO2 molecules will be made by this reaction to get us to equilibrium. And now, the two sig figs, I get 9.4 times 10 to minus 24 moles. Well, I want molecules. I want to count them up individually. So you're here today, aren't you, Avogadro? That's nice. Now we'll get out the push button calculators and do the arithmetic. And I get 5.7 molecules. Do you like that result? I want to see this 0.7 of the CO2 molecule floating around in there. So what am I going to call this? I'll call it 6. Oh boy. 6 molecules, count them up. You think we could do this experiment by actual measurement? I want to see you find these 6 molecules in a volume of 10 liters. So then, from a very practical standpoint, we now know why this stuff, teacher's favorite weapon, is hardly going to fall apart in this atmosphere under the existing conditions. Because this atmosphere, per each 10-liter volume, has got a hell of a lot more than 6 CO2 molecules. Ha! There's a hell of a lot more. Every time we exhale, boom, more CO2 molecules, right? I trust that in addition to inhaling, you're also exhaling. Is that fair? That's good. Because I don't want this room to turn into an evacuated chamber. And the walls will crash in upon me. And then I'm going to blame you. All right? And now, back to the issue you raised. We have recognized, have we not, that this part of the puzzle is for this transformation, isn't it? And what do we do to magnify that part of the puzzle? What do we do to get this reaction to become spontaneous? Let's say under standard state conditions. What are we going to do? We're going to heat the system, aren't we? So then, the issue is, at what T is this reaction at equilibrium? Under standard state conditions. Well, how are we going to find this out?
Plug in to the equation with delta.
Plug in.
Plug in the temperature until you find.
Plug in the temperature. We're trying to find the temperature. How do we plug in something we don't have? That's all right.
Solve the temperature
How are we going to find this temperature?
from the circle star equation.
From the circle star equation. We can't use that. I erased it. And the answer is not from the circle star equation. But that's all right. You responded.
You would set delta HR equal to T delta S.
Delta H0R equals T delta 0, right? Ha! Change in enthalpy, standard state conditions. Change in entropy, standard state conditions. Now, it is true that in doing this calculation, we are assuming that delta H0 and delta S0 are each isothermal properties of this system. What's that mean?
They don't depend on temperature.
Don't depend on temperature. That's almost true. It's good enough for us at this stage of the game. But in an upper level course in physical chemistry or some such a thing, should you get there, or should you be interested in such, you can do calculations to see how delta H0 for a reaction depends on heat capacity. And so you can see how the delta H0 will vary somewhat. Same for delta S0. We're not concerned with that. You'll find out that as long as for a temperature range, phases of components of the system remain the same, then delta H0 and delta S0 will be about the same throughout that temperature range. So whatever temperature we're going to calculate here, we will be a believer that calcium carbonate will still be solid, calcium oxide will still be solid, and CO2 will of course be gas. Well, we know we're going to heat the system, so we know daggone well the CO2 is hardly going to condense. Now then, we got the delta H0 value that we need and the delta S0 value that we need, so we just put that in there, make the unit adjustment, because delta S0 is in joules, delta H0 is in kilojoules, and you will get T equals, you do the arithmetic, 1091 K. But what would you do now if you had a handbook of properties of chemical substances? What would you do now to see if this T seems to be valid? What would you do to see if our decision that delta H0 and delta S0 will remain essentially the same?
And the melting points of board.
Yeah. You look up the properties for calcium carbonate, calcium oxide, and make sure that at this temperature they're still solids. Then we're okay. My memory's right, that holds. So, if we want this reaction to be spontaneous, the decomposition of calcium carbonate into calcium oxide and CO2 gas, if we want this reaction to be spontaneous under standard state conditions, we take this stuff and heat it to what temperature?
1091 K.
Over 1091 K. Because if we're at 1091 K, it would be equilibrium. We want it to decompose spontaneously under standard state conditions. So, we'll write that down. For CaCO3 solid to decomp spont at standard state conditions to become calcium oxide solid and CO2 gas heat above 1091 K in we got to put a word in here. Open or closed? Open or closed?
Closed.
Well, then you just flunked the calcium oxide preparation question. Because if you close this system, you're going to get back to equilibrium real fast. And once you're at equilibrium, boom, end of transformation. You want to do this in an open system, like right here in this room. As long as this room is not sealed, the the carbon dioxide produced by this transformation at a pressure of 1 atmosphere, at a partial pressure greater than 1 atmosphere, because we're going to heat this above 1091 K, will continue to push back the atmosphere, which is at a pressure more or less of 1 atmosphere. So the transformation will continue to take place. And I will tell you, at least last I checked, calcium oxide, in terms of tons produced per year as a chemical substance by American chemical industries, is in the top 10. It's damn important stuff. This is the way you make it. Take the calcium carbonate and heat the hell out of it. A lot of calcium carbonate available here in Florida, for example.
What is calcium oxide used for in industry?
What's it used for?
Yeah.
Well, I'll tell you one of the main things it's used for: CO2 scavenging. Are you surprised at this? If you want to take an atmosphere and free it of CO2, put some calcium oxide in there. Right? Didn't we just find out that calcium oxide and CO2 react really good with each other, say at 298 K? There are other uses for this stuff. I can't recall straight away what the uses are, but you can find this easily if you should be interested. Now, let me remind you, there's a series of questions attached to what we have just considered that you will go through tomorrow in discussion class, and then on Wednesday, we're going to once again revisit this equilibrium system and subject it to thermodynamic analysis, with the intention being of finding out that at 25 centigrade, that baby comes to equilibrium after N2O4 decomposes about 20%. Dissociates about 20%. Remember, that's what our G state graph shows us?